Okay, we're going to spend some time discussing SID, and I neglected to bring my textbook, so I may need to use y'all as a resource for like textbook pages and things like that, but I'm going to try to make this as simple as possible. So here's my learning objectives. Again, these come directly from the textbook. We're going to describe methods for measuring or estimating SID. We'll explain the effect of SID on image penumbra, sharpness, and magnification. We'll calculate exposure changes using the inverse square law, and then we'll also list image qualities not directly affected by SID. And kind of implicit in that, calculate exposures using the inverse square law. It's kind of the reverse of that, which is also be able to apply the direct square law. So, measuring SID. Measuring SID has a substantial effect on on exposure level, magnification, and sharpness of recorded detail. Basically, as SID increases, we would expect to see the exposure intensity drop off. Magnification would also drop off, but sharpness of recorded detail would increase. Okay. Most X-ray tubes have a red X or plus engraved on the anode end of the X-ray tube housing to indicate the exact vertical location of the focal spot, the actual focal spot. This is the point from which SID and SOD should be measured. So it is not from the collimator. It is a kind of a point inside the tube. So don't make the mistake when you're measuring SID of just thinking you can just measure from the collimator to the patient or something like that. We have to, generally, if you pull out the tape measure on a portable X-ray machine or on your machine, you'll see that the tape measure starts at like 11 or something like that, because it's already accounting for that distance. Most X-ray machines have interlocks at the appropriate SID for your department's techniques. And then that should not say already calibrated, it should say already calibrated to the location provided. Sorry, using a dictation. Okay, estimating SID. I always think about the little kid in Christmas Story. I can't put my arms down. Well, if you put your arms out, what you have is basically your height. Right? This distance from here to here is roughly how tall I am. Now, I'm about 6 feet tall, and so guess what? I can estimate a 72-inch SID by just putting my arms out. If you know your height, right, which most of us I hope do, and you put your arms out, you have a way to estimate some distance, right? And then you could just add or subtract from there if you need to. If you need to estimate 40 inches, just put out one arm, right? As a general rule of thumb, it is best thought to use the maximum SID needed for the exam. And again, that's because it's going to improve image sharpness. Oh, let me go back. The effects of SID, like I've kind of alluded to, is that as SID increases, we see a decrease in blur or penumbra, so an increase in relative sharpness. The longer the SID, the sharper the recorded detail. Might be another way of thinking about that. Magnification, as SID increases, magnification decreases. So the goal is generally to use the maximum feasible SID, again, for both those two reasons. All right, well, but let's talk about SID and exposure, right? Another way to talk about this might be intensity of the X-ray beam. As SID increases, exposure decreases exponentially, and the way that we express that is in the inverse square law. I don't like the way he has the inverse square law written out in our textbook. I generally think about it in this way. Unfortunately, when it imported this slide into this lecture software, it failed to do the powers, right? It failed to do the subscripts and the powers. So the way you have it in your packet right there is correct, okay? So that should be intensity subscript 1 over intensity subscript 2 equals D2 squared over D1 squared. So they are opposite each other, hence the inverse. One way to think about it is invert the change and then square it. Right? If you're a more geometrically minded person, it may help to consider figure 22.5 in our textbook. Not sure what page it's on.
340.
Which one?
340.
340, thank you. I like this illustration a lot because it shows a doubling of the SID, right? And at this level, we've got 4 squares, right, where the x-rays or the light are being distributed over those 4 squares. When I double the distance, I now have, 16 squares over which the intensity is being distributed. So I've spaced out the area that's being exposed. It's grown in size, but the intensity in any one of those little squares has just been quartered. Right? So I like those kinds of illustrations because they readily help me see what it is I'm trying to see. But another way to think about it is to go back to the movie Spinal Tap, right? And to think about what your parents were saying when they said, if you want to listen to that garbage, go to your room, right? I don't know if anyone else was into metal music or rock and roll when you were a kid, but if I wanted to listen to rock and roll, I had to go to my room. Why? My parents, whether or not they knew it, were applying the inverse square law to the terrible music that I was listening to. By increasing the distance that they were from the sound source, they were decreasing its intensity. I could listen to it as loud as I wanted to in my room, right? So as they got further away from it, the intensity dropped off exponentially, right? I also like this illustration because if you see, this right here again expresses how with sound sources the exact same thing happens, right? So as we're thinking about things like volume, we're doing the exact same thing. So we can use volume as a way to illustrate the way the inverse square law works, right? So as we further our distance away, we're spreading out the sound waves more. Another way to think about it is like last week we had that guy with the booming bass drive past us on Madison, right? When he's sitting there at the light with the bass going, we can all hear it just fine. But as he starts to drive away, the intensity of that bass falls off. So, let's switch gears. We all know that. That's an established fact. How the heck do we deal with it as technologists, right? What does this mean for my technique? Now I need to start thinking about the direct square law because I'm trying to compensate for this, right? I'm trying as simply as I can put it to compensate for what I know about the fall off in volume or intensity. So adjusting SID alters only the intensity of the X-ray beam. It does not alter the penetrability, right? These things are going at the speed of light, right? It is not as though as I get further away from the X-ray source, the X-rays are slowing down. They are not slowing down. They're just spreading out, right? So it's only altering the intensity. I guarantee you'll see that again somewhere. Adjusting mass restores the original exposure intensity. So I turn up the mass, and I'm just creating more X-rays to make up for that divergence of the X-ray beam, okay? As a general rule of thumb, any change in SID greater than 10% should be compensated for by changing the mass. So it does matter. If the exam was supposed to be done, if the portable exam was supposed to be done at 40 inches, and I didn't measure right and I did it at 50, guess what? That matters, right? It matters. You will see that on your picture, even with the digital system. So there's the formula. Again, like I mentioned, when I imported it, it wasn't correct, but it's correct on your slides. The change in technique is simply the change in SID squared. The change in SID squared. But here's another way to think about it. Go back to the movie Spinal Tap. What are we doing? We're saying if we're increasing that distance, if our parents said go to your room, we're going to go to our room and turn the volume up to 11, right? Because turning the volume up to 11, we just compensated for that increased distance. We're going to do the exact same things with our X-ray machine. If we have to shoot it a further distance due to the way the patient's room is set up, or the technique calls for it, or what have you, we need to make this change. We're going to need to turn up the volume. We're going to need to turn up the mass on the X-ray machine in order to compensate for that distance change. Okay? So you can see I've just taken the same illustration over here with this fall off in relative sound intensity, because sound waves do the exact same thing. So the blue line in this case is the inverse square law. We see as we increase our distance, We have a rapid fall off in intensity. So what do? I set my speaker volume to 11. I turn my X-ray machine's mass up, and I can compensate for it. That's the direct square law in red. Some stuff that SID don't do. There is no direct relationship between SID and shape distortion. Doesn't affect it. Okay? SID does not change beam energy level or penetrability. Okay? So let's drill down into those two because they're both important. First off, with no direct relationship between SID and shape distortion, I've said that SID decreases magnification. So how can I say it doesn't affect shape distortion? Well, what I'm saying is there's not a direct relationship. What it's doing to magnification is it's minimizing that magnification factor only slightly. In a bigger part, it's reducing image blur. Okay? So as I increase my SID, though, I'm not seeing really any changes in elongation or foreshortening, things like that. Okay? It does not change the, again, I'll repeat, the photons that are leaving the tube at a certain energy level, they can travel all the way from Earth to the sun and back, and they will be at that energy level. They are high-powered things. So SID does not affect the penetrability of the primary beam at all. So again, with the sound waves, it's not as though when I go to my room and I'm listening to my music, that all that music's still traveling at the speed of sound, right? All these X-rays are still traveling at the speed of light, so their penetrability has not changed. SID is not considered a controlling factor for subject contrast, so it's not a way that we're going to mess with our subject contrast at all. All right, and that's it.